Welcome, everybody, to watching the rapidly evolving universe. I hope that you and your loved ones are all safe and well in these most challenging of times. My name is Shipsey. I'm a professor of physics at Oxford and head of the Department of Physics. I'm going to say a few words to you about how we're getting on, what we're doing, and then introduce you to my remarkable colleague, Professor Katherine Blundell. So first, I want all of you to know that we in Oxford are safe and well. As you know, the UK recently entered a second national lockdown. But from before the first of those lockdowns, we put in place safety measures against the virus that exceed university and government guidelines. As such, we were well prepared to enter this second lockdown. Among the faculty and the staff, those that can work from home are doing so. About 20% of our colleagues conduct experiments in the laboratory, and they are in the department every day as normal. As are our staff in the mechanical workshop, the electronics workshop, and a dozen other specialist facilities that we operate in the department. We were delighted to welcome 100 new DPhil students in October and almost 200 undergraduates. All that we had admitted earlier that year had arrived. Lectures are online, most tutorials are in person, and we continue to carry out our research online. We write papers, we publish papers, in fact, at a quickening pace. We write grant proposals, we conduct seminars and colloquia, we hold conferences, we hold access and outreach events, and alumni events like this one. So even though our buildings are quieter than normal, the work goes on apace. At Oxford, we seek to bring the transformative power of physics to the foremost scientific problems of our time, from the smallest scales of particle physics to the larger scales of the universe as a whole, and everything in between, unraveling complexity to discover the way the universe is and how it works. Discoveries in physics have formed the foundation of countless technological advances and play an important role in many scientific areas today. Many techniques used in fields as disparate as medical imaging and quantum computing are derived from physics. And even the World Wide Web, which was invented by our former student and Oxford colleague, Tim Berners-Lee, grew out of information processing and communications requirements for particle physics. We work with enterprise and with industry to bring our Oxford discoveries to society. We educate the next generation of leading physicists and engage with the public and with government to educate them on the enabling power of our science. The contributions of physics to solving global problems such as energy production, environmental protection, global warming, and public health are essential and have an enormous impact on our society and on our work. Now, as head of the department, I have the privilege of working alongside truly remarkable colleagues whose research spans the breadth of physics. They include particle physicists who played a leading role in the discovery of the Higgs boson. And just a few weeks ago, one of our students made a major breakthrough in the elucidation of its nature. Astrophysicists who are leaders in cosmology, in galaxy evolution, in the study of pulsars and other transients, the search for exoplanets, and the development and construction of cutting-edge instrumentation. Outside of astrophysics, moving to space instrumentation, we have developed instruments for 16 missions that orbit the Earth and for missions to the Moon and to Mars and to Jupiter and Saturn. And just a couple of weeks ago, you'll remember that NASA's OSIRIS-REx made contact with asteroid Bennu and we've been part of that mission since 2012. We lead the UK national effort in quantum computing, holding world records for our ion-trap qubits for the experimental achievement of all elementary quantum logic operations with a precision of 99.9% or better. And this is the best results ever achieved for any qubit platform. In biophysics, in the last few weeks, you'd have seen a raft of news stories about the ultra-fast COVID-19 diagnostic tests that we have developed, working directly on throat swabs from COVID-19 patients without the need for genome extraction, purification or amplification of the viruses. The method starts with the rapid labeling of virus particles in the sample with short fluorescent strands. A microscope is then used to collect the images of the sample, with each image containing hundreds of fluorescently labeled viruses. Machine learning software quickly and automatically identifies the virus particles present in the sample. And this approach exploits the fact that distinctive virus types have difference in their fluorescent labeling, and this is due to differences in their surface chemistry, their size and shape. Our climate physicists are leaders in understanding, for example, the role of cloud in humankind's influence on cloud. Another aspect of climate change is a drive to achieve clean energy. We hold world records for the efficiency of carboxyte on silicon tandem cells, and our company, Oxford Photovoltaics, is close to having the manufacturing line in Germany up and running. The plan is to have the first modules available for market in the second half of 2021. Another important approach to clean energy is nuclear fusion, turning hydrogen into helium, mimicking the sun. We lead a large international collaboration that has been running a series of experiments to understand how the opacities of plasma produced at high temperatures are affected by temperature in the challenging regime at the interface between our understanding of condensed matter physics and our understanding of plasma physics. So this is very relevant to energy transport in stellar interiors, but of particular importance to inertial confinement fusion research as well. Machine learning is ubiquitous, and we use it in multiple ways. For example, to visualize electronic quantum matter with scanning tunneling microscopes, or to teasing out the properties of elementary particles at the Large Hadron Collider, or to the discovery of new astrophysical objects. Our accelerator physicists lead large international projects to build next generation accelerators that will shed light on how the universe was born and how it will evolve, but also accelerators for the development of public health. And finally, you may have seen our esteemed colleague, Roger Penrose, has just been awarded the Nobel Prize for Physics for the discovery that black hole formation is a robust prediction of the general theory of relativity. Now, looking to the immediate future, we have ambitious plans to expand in climate science, in energy, and to harness the power of the second quantum revolution to improve the human condition. Just as quantum mechanics taught us how electrons move in metals and gave rise to the transistor in 1947 that ushered in the modern age, and has enabled, for example, mobile phones with 1 billion transistors, 1 billion in here. So harnessing the properties of quantum mechanics still further, properties such as superposition, interference, and entanglement, Einstein's spooky action at a distance, will lead to quantum-enabled devices, the best known of which is quantum computing itself, but there is so much more, including a quantum-enabled cell phone, which I can't show you because it hasn't yet been invented. But if you ask me what this quantum-enabled cell phone would do, I would not be able to tell you any more than the inventors of the transistor could have told you or envisaged what a cell phone could do. But that is a promise of the second quantum revolution, and Oxford is at the heart of it. Now, if I had more time, I could tell you so much more about the astonishing work that I see around me every day, about Oxford scholars doing remarkable research made possible by alumni support, about the search for the inaugural Professor of Biophysics that we're just conducting now, a position made possible by alumni, about students and faculty creating startups at an accelerating rate, 5 new companies in 2020 alone, a wonderful new course on enterprise and innovation, our new Oxford Access programs that work with high school students from families where nobody has been to university before, and outreach programs that have reached more than 200,000 people in the past 5 years. But time is short. We have some of our development team here today with us, including Lisa Wilmot from Oxford. And I think some of you know her already. The role of development teams is to raise funds, which help make some of the incredible research that I've just described and that you'll be hearing about in a moment possible. We're not here today to ask for such support, just to give you an opportunity to immerse yourself for the next 80 minutes in the exciting world of physics. But if you are inspired by what you hear and would like to know more, then our development team, Katherine and I, would love to speak to you. So now it gives me truly great pleasure and privilege to introduce to you today's speaker, Katherine Blundell, a professor of physics here at Oxford and a brilliant astrophysicist. She is also the Gresham Professor of Astronomy, a position once held by Sir Christopher Wren. She has written over 200 papers in international journals in works that span the entire electromagnetic spectrum, from the radio to X-rays, with a particular focus on extreme objects, such as those that are very hot, very interacting, very energetic, or very explosive. Katherine is particularly interested in studying objects in the universe that change remarkably rapidly, understanding and elucidating how this change or evolution comes about is a focus of her study. And this field is now known as time domain astrophysics. Although many astronomers working in this field and in other parts of astronomy use large facility telescopes like those sited in Chile or in Hawaii, with telescope time shared between many, many scientists. As part of Katherine's research strategy, she has not only used such facilities, but has herself developed a new set of facilities, a network of telescopes distributed around the globe. And this means that she can do around-the-clock monitoring of these changing processes. And in this talk, she's going to describe exactly how this works and provide new insights into our surprisingly dynamic universe. Now, I believe all of you are muted, and so you won't be able to now join me in a round of applause to welcome Katherine, so I'll do that on your behalf. It's a great pleasure to present to you today my colleague, my friend, Katherine Blundell, a brilliant astrophysicist. Welcome, Katherine.
Well, thank you very much indeed, Ian, for your very kind words, and I hope that you can hear me okay. Well, hello everybody, and thank you so much for joining us on this rainy Saturday evening. It's my honour and my pleasure to be able in the next hour to share with you some of the research that I'm passionate about, that it is my privilege to investigate here in Oxford and beyond. Well, many of us have the sense, I think, that the night sky is a very beautiful place. And some will say that the night sky is serene and static. I will absolutely agree that the night sky is a thing of beauty, a changing thing of beauty, but I will profoundly disagree with the statement that it is serene or that it is static. Not a bit of it. We do know that there are patterns and rhythms in the night sky. And I hope that you can see here what happens as we capture images of the night sky through a fisheye lens on an all-sky camera. You see the sun rising in the east and setting in the west. And this reminds us of the rhythms that we see in the night sky because we live on a spinning planet. I hope you can see Orion lying astride the galactic plane, crossing from left to right. And then morning has broken, the sun also rises in the east, passes through solar noon, and then sets over in the west. And so we have evening and then nighttime, which is when we can get to work and do our investigations when we're not hindered by a storm, that is, which is what you saw just there. So let's take a little look at our own galaxy, the Milky Way. It's a beautiful place. At first glance, it may give the impression of being static, serene. Not a bit of it, as we'll see later on in the talk. I want to take you to a part of it. I hope you can see the red rings that have just appeared there, to a particular point in our galaxy. While we're looking here at an optical image, one just taken with a fairly normal digital camera, I want to take you to what that region of the sky looks like if we observe it at radio wavelengths. It's a bit of a scruffy image, but perhaps you can see in the lower middle part of the image, there's something that looks a bit like a conch shell pointing upwards, trying to drive itself nose first into the plane of our galaxy, which is what that main stripe is, going from lower left to upper right. If we zoom in on that conch shell structure, again remaining at radio wavelengths, we see something of a remarkable structure. Part of that structure is described remarkably well by a circle, and it's circular because it reflects the spherical symmetry which happens when a supernova explodes in the galaxy. The bits that sprout out to the left and to the right, well, we'll understand where they come from a little later in the talk. So this is a radio image. It came from a telescope known as the Very Large Array, affectionately known as the VLA, and it's perhaps famous because it starred alongside Jodie Foster in the movie Contact. Radio astronomy gives us many great insights into the evolving nature of the universe. And if I zoom in now on that same structure that I was describing to you, which spans something like 2 degrees in the sky, that very central point, well, that is distinctly different. In fact, it arises because of plasma that is squirted out in opposite directions from very close to a black hole at its very center. That's the black hole which gave rise to that big circular supernova explosion that I indicated to you a few slides ago. If we zoom into that lower image further still, then again, we see a closer indication of jets which squirt out in opposite directions from that central black hole. That inner view of that very innermost part of the radio jet coming from these black holes was taken with a telescope that spans the continental US. I've color-coded it in subtle shades of grey because I think we've seen quite a lot of red and blue colouring this part of the world. But the geographical distribution of these 10 radio antennas enables us to produce images that speak of the temporal evolution, the time evolution, the changing nature of this particular object. And in fact, we can set movie, if we can take time-lapse stills by repeatedly observing the same bit of sky, then we start to get a sense of the jet actually squirting out these blobs of plasma. And I wonder if you have a sense that maybe the directions along which the plasma is launched changes with time. Each still in this movie corresponds to, excuse me, 1 image per 24 hours. And this is obviously speeded up because we don't want to be here all night. And so by making time-lapse observations, we get a very good sense of how this particular bit of the galaxy is changing with time. Where do these plasma jets come from? And how on earth do they manage to squirt out in these opposite directions? Well, that particular question is one of the $10 million questions in this particular bit of physics. We have very good reasons to believe that there's a big black hole at the center of this object, and that its mass is something like 25 times the mass of our sun. If we could zoom in much, much more finely and look at optical or X-ray wavelengths, then we would see something a little different. We would see that there's a normal star that's very closely connected with the black hole. And that normal star we would see being ripped to bits by the gravitational attraction of the black hole that's at the center of this red holding pattern, this red disk of material that is being accreted onto the black hole. Now, black holes are very, very messy eaters, and they squirt out material perpendicular to the direction in which the material is spiraling in and swirling in as it's being sucked by gravity. So we know gravity is a big part of what's going on. But let's go back to that radio image that I showed you earlier, the one with the zigzag curly corkscrew shape that I showed you a moment ago. If I could make a time-lapse image of that rather funny shape that I showed you a few minutes ago, you would see a rather unusual type of evolution. Such a movie as I'm showing you now would be possible. Nab the VLA radio telescope all for myself and prohibit all other astronomers on the planet from using it. And if I could color code the material coming out of your screen towards you blue and traveling away through your screen away from you red. But I can't do either of those things. So this little cartoon movie, which I've coded up on my computer, is the best that I can do for you. If we were in a position to make time-lapse observations, we would see this kind of evolving and revolving with time. What's actually happening here is that packets of plasma, highly energized hydrogen, are being squirted out from away from the black hole along an axis which itself precesses with time on a timescale of about 6 months. The picture to have in mind is that this axis that's changing in time is changing like the paddle of a kayakist in the rest frame of the kayak. I hope you have a sense of the way material is driven off from that accretion disk, which itself is changing in directions as it launches the highly energetic plasma, moving at speeds comparable with the speed of light. This is the picture that we have, but how can we go about investigating this? How can we go about exploring the nature of how matter is attracted towards the black hole and then ejected from it and squirted away into the galaxy, bursting through that circular spherical shell around the supernova that I showed you earlier, that had elongated to show those ear shapes? Well, radio astronomy isn't the route to do that, because we can't monopolize it and make our time-lapse observations. What we can do, though, is to point an optical telescope right at that central point, at the launch point of the red and blue squirty toothpaste that's coming out, and we can consider what that reveals. So I'm showing you now an optical spectrum of this exact same object at the launch point of those jets of plasma that get squirted out. A spectrum is what happens when we disperse into colour or into wavelength the light collected by the telescope. Much the same thing happens when a rainbow, water drops in clouds disperse light from the sun into a rainbow. What's going on here is that our instrumentation disperses starlight into a spectrum. And what you see here is a great big spike in that spectrum, color-coded here green. And what that's saying is we're getting a lot of light from excited hydrogen atoms. The line on the blue, on the left, is what we call blue shifted H alpha. That's light from hydrogen that's whooshing towards you. And on the right, we have red shifted H alpha that is whooshing away from us. Now, intriguingly, these change with time as the jets are launched, as the jets change in direction. And this comes very, very simply from the Doppler effect, something that's very familiar to physicists. If you take, for example, an orange emitter of light and you blast it away from us, then what you would see as orange light, if you were clinging to the street lamp, is seen red if it's on a spaceship whooshing away from us. Now, in fact, this object, as it changes direction with respect to us in the way that it launches the plasma away from the black hole, the oscillation around the way that processes has been known since the late 1970s. David Clark and Paul Murden did some of the first seminal observations. Andy Fabian and Martin Rees cracked some of the important theory. But where it really first came to public knowledge was when reports of this object appeared on Saturday Night Live. I would say it was something of a garbled explanation. In fact, quite a bit of that episode was somewhat garbled. Margaret Thatcher appeared on that episode of Saturday Night Live, but she was played by Michael Palin, so it was all a little bit garbled. Now, in fact, and let me just very, very briefly mention that we can mathematically describe the behavior of the launch speed of these jets. And from one single spectrum, we can pull out what is the launch speed of the plasma. So what we do with a spectrograph, we take an observation at a single instant of this object, and with this mathematical machinery, we turn a spectrum into a speedometer. We've got a different configuration of these equations that gives us the launch angle of the plasma that's spat out from near the black hole. So armed with that velocity vector, and also with information from that central green line, the so-called stationary hydrogen line, which isn't stationary at all, but it doesn't move in the way the other lines move, that wiggles around and tells us a lot about the material that's sucked in and attracted towards the black hole. So in principle then, we've got something evolving rapidly, and this object shows variation on timescales of hours, as I'll show you in a few minutes. We've got mathematical machinery to unpack the relevant physical quantities that we want to know, but how do we get hold of the astrophysical information that we want? If you apply for time on one of the major telescopes, one of the worldwide facilities that Ian mentioned in his introduction, then you might be lucky enough to get, say, 4 or 5 nights on this telescope. And that would mean that for the duration of darkness at the location of the telescope you've applied for time on, you can study your object as it rises and it sets. The y-axis that I'm showing here can be thought of as observability. It's telling you how far a target is above the horizon. And you'll see immediately that there's only a relatively small fraction of each 24-hour period when you can actually follow a particular object or anything else in the night sky from that single location. It doesn't work if you want to study objects that evolve on sub-24-hour timescales. And so I began to realize if I wanted to make serious inroads in this area, I would need to have telescopes distributed all around planet Earth, separated in longitude, so that there is always at least one of them in darkness. And so without this, it wouldn't be possible to follow round the clock the attraction of matter towards the black hole systems we're studying and the ejection of matter around the black holes that we're studying. So this particular graph represents our observability, the availability of our ability to observe the night sky with telescopes at the locations that I've listed. What are those locations? Well, let me tell you now about the Global Jet Watch, which I set up to pursue these kinds of investigations. So, as we all know, the Earth spins and the Earth rotates. And if you can imagine towards the top left, a particular target in our galaxy, the Milky Way, which is the stripe that goes across the movie that you're looking at. each location on Earth, each longitude on Earth, takes it in turn at night time to be able to view that particular part of the galaxy. And so you can see that there are telescopes. Chile is the one now pointing at the target I mentioned in the galactic plane. We also have telescopes in southern India, in South Africa, and on the left-hand side of Australia and on the right-hand side of Australia. So this deployment of observatories means that we can do round-the-clock astronomy, not just of things with periodic patterns, which aren't always that periodic, they're pretty explosive as well, but also of significant stochastic events in the night sky, such as nova explosions. And one day we hope the next galactic supernova explosion when that happens. How do you go about building telescopes like this, or a network of telescopes like this? Lots of concrete, lots of broken fingernails, and lots of time and sheer hard work. But hard work does pay off. This is a picture of the top end of my telescope in Chile, looking out on the night sky there. It's early afternoon in Chile right now, but this was obviously taken when I was at the telescope. This is the back end of that telescope, and you can see the optical instrumentation we have on the back. It's all mounted on an instrumental manifold, which enables me, from the comfort of this particular seat in Oxford, to be able to switch the optical path from imaging and the acquisition of a particular target to spectroscopy. And that works beautifully and very, very straightforwardly. But this telescope has at the back, what you're looking at now is the fibre injection and guiding unit on the back of the telescope. That's connected by an optical fibre down to this shiny red box, which is a spectrograph. What's a spectrograph all about? That's the instrumentation that disperses the optical light collected by the telescope into a rainbow or a spectrum, this thing that with our equations we can use as a speedometer. The dispersing element isn't raindrops in a cloud, which is what we have in the case of a rainbow, but it's a volume phase holographic grating. And that enables, by periodicities in its refractive index, to give us a very high throughput instrument, so we don't waste any of the light as we collect it. This was designed and constructed by my colleague and friend Steve Lee, who's a senior technician at the Anglo-Australian Observatory. So this is one of our telescopes. This is the one still in Chile, sort of side-on view. And then this is from underneath, showing some auxiliary cameras that we have rigidly bolted to the optical tube assembly. We collect lots of other data streams besides spectroscopy. Time-lapse spectroscopy is the powerful tool for anything where you want to study the dynamics, the explosion, or the evolution of anything that's changing. But having onboard photometry really is a very, very powerful tool as well. So these are all the Global JetWatch telescopes, and I'm delighted to say that they're working well. Despite the pandemic lockdown earlier this year, we stayed on sky. A good many other observatories had to close because of the dangers of people working in close proximity. But I'm thrilled and delighted that there wasn't a break in our data streams. How do I keep in contact them when I'm here in Oxford, which of course I'll be for some months until I can get out to the observatories again? Well, thanks to a wonderful hardware VPN made by Sophos, the cybersecurity company based in South Oxfordshire, and to avoid the darker side of cyberspace and to protect the integrity of our telemetry, we have that every computer in each observatory, every IP device thinks that it's connected to the Oxford Department of Physics via an Ethernet cable, albeit one that's several thousands of kilometers long. So we can robotically control telescopes in different parts of the world. And indeed, since I've started talking to you, I've just finished observing in Australia, and now that telescope has parked and its observatory has closed up because the sun has just peaked above the horizon. Well, before I tell you about some of the scientific endeavours of the Global Jet Watch, let me share with you some of the spin-offs that were part of the design of the project from the absolute outset when I first dreamed up what I wanted to do with this strategy, as Ian said, for doing this kind of research in time domain astrophysics. The original 4 observatories are all located in residential schools, and I'm showing you here the observatory that's in our school in rural southern India. The paradigm is that before local bedtime, the school children are absolutely free to use the telescope for themselves. Obviously, once they go back to bed, I log in and operate the telescopes from here or from the department when it's possible for me to be there, and collect data for the research programs that I lead here in Oxford. But it's super important for me that I am not the only beneficiary, or my research team is not the only beneficiary of what we're doing. A big part of how we do what we do is that teenagers are able to operate the telescopes for themselves so that they are able to learn skills and not merely be spectators. Now, being in an observatory and pointing at different targets in the night sky is a wonderful opportunity for these teenagers to have fun. And when teenagers are having fun, they're in a place where they can learn. And so I'm really very, very happy that this enables those students to be able to do that. I'm showing that picture a moment ago was from some schoolgirls at the school in South Africa that plays host to my observatory there. These are some of the Indian schoolgirls wearing their pink shower kameezes as they do in the evenings. One day, one of these girls came to me. It was during the afternoon. I was doing some job or other in the observatory. I had a cordless power drill with me. I can't remember what the job was that I was doing. But this girl and a couple of her friends put their heads around the door of the observatory and said, "Madam, madam, can we ask you a question?" So I said, "Of course, you can ask me anything." And so they said, "Madam, you're here alone in the observatory. How come you're not afraid to be here by yourself?" And so I replied that I wasn't in the least bit afraid, but why did they think I might have been afraid? Their reply was startling. "Because of the machinery and all, madam. What if the telescope jumps out at you and attacks you?" And I explained to them that the telescope moved like a ballerina, that it was completely under the control of the control computer on the outside of the observatory, and that was completely under their control. And so I invited them to come back when it was dark, which they did. And that night, they were, for themselves, exploring craters on the moon and having fun and not being afraid of technology. In this part of the world, the technology to them means machinery that can maim. And so embracing the next generation into science and technology and engineering involves the elimination of fear. And I'm very happy to say we don't have fear in the observatory. We have gasps of amazement and excitement, and that's really super. This particular school where my India Observatory is hosted was founded by the government of India so that the bright children of rural families who would otherwise be working on the land, harvesting rice, can receive a formal education. Over 50% of the children at this school are first-generation literates. They know that they have an amazing opportunity and a fantastic privilege. And these girls in India have a thirst for knowledge that I have not seen paralleled anywhere else in the UK or in the wider world. If ever there was an epoch in human history when it was time to raise up the next generation of scientifically literate and globally astute young people, I reckon it's about now. Obviously, I can't clone myself. I can't be at all my observatories all at the same time, though I wish I could clone myself. And so Skype or Zoom is previously how I was keeping in touch with them. This is a picture of the very first two girls at the South Africa school, Katie and Jenna, as they observed from that telescope. You may recognize the bookshelves in that photo there behind me now. So the middle picture is where they first controlled the telescope for themselves, and that's when they started looking at their first galaxy. It's made a big impression on them. And Jenna, the one who's got her hand on her chin, she went off to, she is now studying at the University of Cape Town on physics with astronomy. And she's just choosing now what postgraduate course to do. And she attributes her enthusiasm for science and pursuing science at a higher level to the opportunity of having a telescope at school to play with. Of course, I encourage play, I encourage exploration, and that's been wonderfully fulfilled for a good many different schools. The wonderful things about schools is that every new academic year, there's a new cohort that replenishes those who leave. This is Magisha and Lorraine, who, again, this was another interaction by Skype that I had. Before I tell you about some of our scientific results, I will just share with you this email that came from a child at the India school. Dear Madam, hope you saw the image of Jupiter. It was magnificent. We even saw, that's a list of different targets that they observed. Guess what, Madam? Every night in my dream, I play only with stars and nebulas. Once I enter the observatory, I forget everything. I feel I have entered heaven. This is a school where they have one flushing toilet, and the laundry facilities are stones that they whack the wet cloth onto. And it's an absolute treat to be part of all of those schools all around the world. And I miss them greatly, and I can't wait to get back to them. Now, setting up the different observatories, pursuing the dream of time-lapse astrophysics has not been without its challenges. And I'm not merely talking about the challenge of scarcity of resource for such an ambitious operation, or of sustaining night-by-night operations. I'm talking of challenges both large and small. This is one of the small ones. Squirrels in India have really sharp teeth, and they like snacking on all sorts of things, such as focus cables. It was something of a challenge to have to repair this focuser cable, and my mid-air soldering improved no end, because there was no other way I could focus the telescope without doing so. But if you think this is a bit of a challenge for operating a telescope, and it was a reminder to me that this is part of everyday life and the everyday challenges for people in that part of the world. Around the same sort of time that my focuser cable got vandalized, 200 mattresses at the school were destroyed by squirrels. Another big problem with operating the observatories, especially in India, but also in South Africa, is that the power would just disappear. The lights would go out. That is not such a bad thing for astronomy. But the electricity turning off means no internet, means no computers, means no observing those rapidly evolving objects in the night sky, missing out on the early stages of explosions that I'm trying to track. But even when we did have mains electricity in India, it would be dangerous and it would be spiky. Indeed, it would be camera-fryingly bad. I have a collection of the cadavers of cameras blown up by spiky electricity. And one time I decided I couldn't stand it anymore, and I managed to raise the money to build a solar farm at the India School Observatory. Now, again, while unreliable electricity is very challenging for time domain astrophysics, it is absolutely part of everyday life out there. In South Africa, even now, the electricity gets turned off for hours, many hours sometimes in a day. Lack of electricity means lack of communications. It massively hinders development if you lose all these things. And solar energy is such an important way of obtaining a source of electricity that is reliable as the rising of the sun, morning by morning, as I showed you in the movie at the start of my talk. So this is the India School Observatory again, and towards the top right is a bit of flat roof. And the school principal kindly gave permission to me to build a solar farm up there. And so here are some pictures of that process. This is the horse that delivered the steel with which we built a compound, a battery, a shed to store the batteries, which store the chemical energy we collect from the sunlight. Bit of a manky horse. The guy standing there is Sadek. He welded that battery shed for me without him and me having a language in common. He speaks Urdu, I speak English, but we built a fantastic shed. Here inside the shed, we have lots of regulators. We did everything in a super safe way because, of course, it's not monitored. We can't be there the whole time. And so we wired everything very, very carefully. We took no shortcuts in the safety because, of course, children are around. So 3 of us built this with the help of Sadek and another chap, Romulo, myself, Steve Lee, I also mentioned, and his colleague from the AAT, Chris McCowage. We checked everything super carefully. We have these huge lead acid batteries. Wonderful thing about lead acid batteries is they're really heavy. You can't steal them. What you're looking at here is 500 amp hours in a battery rack. We have 4 of those. So in total, we can store 2000 amp hours of battery. So this is all in a battery shed vertically below the observatory. And these are the steel stands that were welded to support the solar panels, all up there on the top roof with the observatory. It was extremely hot, hard work, hammer drilling those steel frames onto the school roof. I was helped a little bit with Romulo there, who would pass me bolts faithfully the whole time while I was doing all that hammer drilling. But I think by the time I'd finished, I drank 3 litres of water straight off. But we did it. We've got 12 square metres of photovoltaic panels. We are completely off grid. And the school children at this school now know and understand that the observatory is entirely powered by light from our nearest star that we gather up by day in order to we store up that energy in those big batteries to be able to study all sorts of interesting and evolving stars across the galaxy by night. As a consequence, the school then began a campaign which they called Go Green Before Green Goes, which is ever so important for raising the awareness of children having a sense of the fragility of our planet. Many of my colleagues in the Department of Physics, as Ian mentioned in the introduction, are doing wonderful research in climate physics, but this is playing a wonderful role getting the word out. Seeing is believing for so many people on this earth, and for impressionable teenagers to see that after installation, we get energy for free out of the sky, which sustains us as reliably as the rising of the sun morning by morning. But the biggest problem and the worst moment and the greatest challenge of all happened at my school observatory in Chile. A loud rumbling noise was heard, and then the ground began to shake. This particular school observatory is surrounded by beautiful mountains. Normally, those mountains are static and serene, not on this occasion. The mountains and the landscape began to flex. It was a major earthquake. It was not a good time to be at the top of a ladder 4 meters above ground, which is where I was. I was inside the observatory doing a job on the very top of the shutter control. A lot of people asked me, what do you do when you're at the top of a ladder in an earthquake? The answer is simple. You get down swiftly and without delay. And that's what I did. But for the next almost 4 minutes, I could not stand upright. I had to grip onto a fence because the rapidity with which the ground shakes in a major earthquake is just huge. The acceleration and the deceleration is not something, when it's sufficiently strong, that the human can withstand. This was a magnitude 8.4 earthquake that occurred a few years ago, one September evening. And apart from the fact that the telescope flopped around, much like a flower on the end of a very fragile floppy stem, my main recollection of that time was walking back from the observatory when it was over to the house where I was staying. I stay in the home of the IT teacher there when I'm visiting this observatory. It's about a 3-minute walk from the school, and the streets between the school and the house of the IT teacher and the music teacher, they're married to one another. The streets were filled with people all crying because of the horrendous experience that had happened. Well, no one in that town lost their life. I managed to get back on Sky just 25 hours later, but there were quite a few problems. The observatory wasn't designed to withstand a magnitude 8.4 earthquake. But this may have been a bad thing for being in the privileged position of collecting time domain astrophysics data, but it's everyday life for people in that seismically active part of the world. We do live on a dangerous planet, and that's a particularly dangerous part of it. But despite all the challenges, we get fantastic data from this this revolving, spinning network of telescopes distributed in longitude around our planet. And so here is one of the spectra that I showed you earlier with the different features that I indicated. Blue on the left coming towards you, red on the right going away from you. Every time you look at this object, it changes deliciously with time. If you observe only once per 24 hours, you miss out on the action. So the spectrum that I'm showing you here is the burgundy spectrum is one night, and then blue is 24 hours later. And you can see that there are significant changes. And if I feed the positions of the red shifts and blue shifts of those complexes into my calculations on my computers, those changes are dramatic. So without following these evolving objects round the clock, we would miss out on the action. That very central line that I mentioned, the one that I said was to do with matter orbiting around, potentially being sucked in, well, that's been known for a number of years to change on timescales of the orbital period of the black hole and the normal star that are orbiting one another, feeding that accretion disk that gives rise to the launch of the jets that I mentioned earlier. Now, for a long time, it was believed that the dynamical situation was that these changes in the lines arose from purely the stars orbiting around one another. But the movie that I'm showing you draws attention to the fact if you don't have sufficient spectral resolution, if you're not doing a clever enough job of your time-lapse spectroscopy, you can completely misconstrue what you're seeing. And in fact, we were able to show that this stationary hydrogen complex, you can deconstruct into different individual components, plot out how those components' positions change with time, and you can find that some of them wiggle, that broad one wiggles, the other two remain absolutely stationary and static in wavelength. That's telling us about material that's outside of the binary, that hasn't yet got sucked in. And I hope you can see it depends a bit on the transfer function of your computer maybe. That great sort of yellow-green vertical stripe going up your screen, that's the stationary H-alpha line, and there are some wiggles superimposed on that. And maybe also you can see the wider wiggles of the jets moving in and out, as I said, on a timescale of about 6 months. If I zoom in, you can perhaps get a sense of material in the center squirting off. It's actually not material squirting off. It's squirting off in wavelength, but a more extreme wavelength means that you're getting much, much faster as you're getting closer in. And we've been able to demonstrate that once you get material that gets faster and faster in that very, very central accretion disk, whoosh, off it goes. And putting these equations that I showed you earlier into the mix, we get, I've stacked hundreds of spectra here just from one 6-month period. If you plot too many in this way, you actually can't see all the motions that are happening. But if you take example individual spectra from throughout the collection of data streams that we've been building up, then you start to be able to use those equations. And interestingly, you start to be able to make predictions about what you ought to be able to see. So I did this, I gathered spectra that had been observed by all of these round the world telescopes in the Global Jet Watch. And you can see that the lines either side of that central bright stationary hydrogen line, so-called stationary hydrogen line, move from different parts. And what I'm showing in this plot, the red and the blue points, are predictions which come from knowing the dates on when I took individual spectra. That bit's really easy. And then taking those positions in wavelength of the spectra as they move around, calculating the velocity vector of the plasma that's launched from the black hole, knowing the date as I said that I did it, and making a prediction for further in the future, what should this look like? What should it be? I then used time, I was awarded time on the ALMA telescope in the northern desert of Chile, Chatnantur. This was observed 2 weeks after that big earthquake that I told you about, but thankfully this telescope was very, very far away. My telescope, my school observatory, was a mere 40 odd kilometers away from the epicenter. And we did suffer a bit of damage. This ALMA telescope, very little damage indeed. And so it was possible to take a radio image on a particular date in late September 2015. And then that tells us exactly what the trace of the jet is. My optical spectra give me, as I say, this prediction, which I'm showing you in the middle panel here in blue and red points. And that enabled me to test out my prediction of whether or not my equations were doing the right thing. And the answer, I'm very happy to say, was absolutely yes. And so it's been really fantastic to study the evolutionary change of matter that's accreted in, sometimes very suddenly, and that happens in a very stochastic way when it whizzes in, and then material is sometimes blasted out in big gulps. But there's a very steady persistence of the pattern of these jets. Another target that we absolutely love to study, we love explosive things, we love dynamic things, we love things that change, is explosions, as I said, of novae. And those change on timescales of tens of minutes, and it's a real treat to study those as well. The night sky is a vibrant and dynamic place, and I hope I've given you at least a very mild sense, a brief window into the fun that it is to study the evolving universe with equipment that was strategically designed to do the job and do the job really well. As Ian said, if you'd like to join us, please do get in touch or take a look at our website. I've given a link there for a little 3-minute movie on what we're doing. But I do hope this has given you an insight into the kinds of things that we're researching on and how we go about that. And with that, I will now hand back to Ian.
Katherine, thank you so much. That was truly a beautifully structured lecture, telling a remarkable story for all of us, of science, of technology, of spanning the globe and engaging with young people across 4 continents, introducing them to the technology and adventures in science. Thank you so much indeed. And now we'll take some questions from the audience. And Katherine, I think you can see the Q&A window yourself.
I can indeed.
Great. So if you'd like to call out the question and then answer it, that'd be terrific.
I'm just doing that now. So there's a question from someone called Pete Briggs, who's asking if the university is undertaking research into dark matter. And the answer to that question is most definitely yes. Ian himself is one of those people, but others of my colleagues in astrophysics are trying to understand dark matter from a theoretical viewpoint. The question goes on to say, is there any evidence that the black hole at the center of our galaxy is also consuming dark matter? Well, the answer to that question, we don't have any evidence of that at present. What we do have evidence of is the fact that that black holes do suck all this illuminated matter towards them. But as I say, they eat in a very, very messy way. And what we're trying to do is, from the pieces of the jigsaw where we see the matter that's spun off and spat out and flung out, we try and piece back to understand exactly what does get consumed by the black holes. I should perhaps take advantage of the opportunity to mention that this is by no means the only black hole system in the galaxy. On the contrary, there are probably millions of galaxies, millions of black holes in our galaxy. And some of the auxiliary cameras that I showed you are designed to collect data streams, which we are in the process of analysing in order to find more such black hole ejecting systems. I wonder if you might like to see, I wonder if I can play this as a movie here. I'm not sure whether it's actually going to play as a movie, but here we go. Let me play it again. The changing emission lines that you had a sense of going backwards and forwards across the spectrum as the jet axis was processing with time, give rise to a signature that you can hope to discern and pick up and analyze from photometric signals, which look at different parts of the spectra. So in answer to the question that I see from Tolga Jack, by no means is this the only specific microquasar that we're observing. We're searching for new ones, making use of this behavior that I've indicated with this movie, the fact that these lines move in redshift backwards and forwards across the spectrum is the means by which we're looking to discover more of them. But we are studying a great many others. So Tolga, the answer to your question is a great many. Now, another question from someone who is remaining anonymous: would a seismic base insulator below the building or the observatory help to protect the observatories? I apologize if this is a silly query or suggestion. First off, in my observatories, there is no such thing as a silly question. A good question is a question you want to know the answer to. So that's the second part of what you've typed. It isn't a silly question. It is realizable in theory, but no way do I have the funds for it, sadly, to be able to do that. But you're absolutely right. You could hope to design a seismic base insulator. One of the fascinating things that's different between watching what happens when there are earthquakes in, say, California or Japan, compared with a place like Chile, is the build quality is much, much, much lower and much poorer. In Chile, when there's an earthquake, if people are wealthy enough and their houses are made of nice flexible material like wood, their houses stand. But ever so many other people with much poorer building quality, their houses go splat. So seismic insulators are a really wonderful thing where they can be, or flexible buildings where they can be included. Another question here from Henry Tebbs. Could you use these telescopes and spectroscopes to study chemical compositions of the moons of Jupiter and Saturn, and also exoplanets in the galaxy? Henry, absolutely yes, we totally can. And studying Jupiter and Saturn and the moons is something that the schools absolutely love to do. I long to have a bit more workforce resource to be able to study exoplanets. We've got data streams that are some of the photometric data streams that I was alluding to with my auxiliary cameras are absolutely optimized to search for candidate systems with planets that orbit around outside of binary systems, even those containing black holes. These are called circumbinary planets. And that's something that we long to do more of in the future. So Henry, thank you for your question. Question now from Jasmine. What is the best idea we currently have for why these plasma jets are expelled from the black hole? Thank you for that, Jasmine. We are always obliged to obey the laws of physics. There are a good many laws of physics, and we understand some of them in great detail, at least at some level, like gravity means that apples from apple trees go splat on the ground, things like that. Gravity is the means by which matter is attracted towards the black hole. But there's also the law of what physicists call the law of conservation of angular momentum, things that are swirling around one another. If something is spinning around something, there will be a characteristic of that orbiting that is preserved. It means that if something gets closer, it'll get faster. Now imagine what happens if you get faster and faster and faster. If you're getting so close that you're on the point of exceeding the speed of light, then maybe you're just going to be squirted out sideways along the pole of the angular momentum vector of the material that's being sucked in. We don't have a detailed answer yet. What I can tell you is that a result of the Global Jet Watch, we've now got a very clear picture of the fact in this black hole system, matter is launched from that accretion disk, that red holding pattern of material that was swirling in towards the black hole. We now know the jets are launched from that innermost region as a result of some of those things I was showing you, where there were lots and lots of spectra together, and you saw material on that central line whooshing off, of course, meaning whooshing in, and then later giving rise to the jet ejector. Question from Patrick Butterley. Presumably the ejected matter hasn't crossed the horizon. Absolutely right. There's no possibility of any matter that's pervaded or penetrated the event horizon ever coming out again. That's a big no-no. That's something that Roger Penrose, whom Ian mentioned as having recently won the Nobel Prize, one of the many things that he demonstrated. So the fireworks that we see occur close to but outside of the event horizon. Question from Louis: how did you choose which of these systems to observe in detail? It's a combination of factors. A good many of the systems that I study, I'd studied in great detail at radio wavelengths, but then then I realized the limitations of doing radio only studies, and I really wanted to do this kind of round the clock study. So I'm studying a lot of the objects that I've studied from radio wavelengths, particularly this micro quasar that I've talked about tonight. But basically, whenever I get a text on my phone saying that a nova has gone off, then I slew whichever telescope is awake and observing and capture data on that. In parallel, I've got these programs that I mentioned to discover new black hole systems in the galaxy, which are ejecting jets similarly, so that I can make studies as a function of black hole mass and black hole spin and that kind of stuff. Question from Nick: how would space-based observations from orbiting satellites help me? That would be great, because we don't get clouds in space and it doesn't rain in space. So that would be super, but way beyond my budget, sadly. And I think we're more or less at the end of questions that haven't already been asked by one or other person. So I don't know, Ian, if this is a good time to hand back to you.
Katherine, I thought you answered those questions so well. If anyone has any last question they would like to put into that Q&A box very quickly, you have a few seconds to do so. And while we're waiting for that, I want to call out a few people to say thank you. The first is to Steve Tup-Jorgensen for his technical Zoom support and knowledge. The second is Liz Ndako, who is our head of communications, has provided the technical backup and co-hosting of this event today. The third person is Lisa Wilmot, who heads our development efforts. And the fourth person is Val Crowder. Val Crowder heads our alumni activities, and in addition, oversaw the entire organization of this event. So a big thank you to all four of them. Are there any more questions appearing, Katherine, in the Q&A window?
I think not that haven't already been addressed, I think.
Great. What I am saying are people are saying, thank you so much. And that's exactly what I want to say now. So thank you for that talk. For me, it was 80 minutes of science and pure inspiration. Thank you on behalf of all of us, I'm sure. I'm speaking when I say that. So finally, everybody, if you want to know more about what you've heard tonight, please contact Katherine, myself, or Lisa, and we'll be happy to tell you much, much more. So stay well, stay safe wherever you are around the globe. Remember, Oxford Physics is great. Our scientists are great, our staff are great, our students are great, and you saw a perfect example of that tonight. Katherine Blundell is changing the world. Thank you very much. Bye-bye.